All right, we're recording now. So let's begin today's class. In the previous class, we had discussed difference equations and how time series economics involves the estimation of stochastic difference equations. So we had begun with the Ar1 model or process, and we discussed how to find the solution if you have a first order difference equation, how we go about finding the solution to that. So in that context, we discussed two methods. So the first method involved iteration, where you continuously keep substituting and moving forward in time, okay, by substituting the values of y1 and y0 and so on. Okay. So by continuously iterating forward, we are able to arrive at a solution to the first order difference equation. That was the first approach that we had discussed. Okay, and that is assuming that the initial condition is given, okay, that at time t equals 0, the value of y naught is given to you, then you can use this method of iteration and arrive at a solution. That was the first method which we discussed. Then in the second method, suppose you're not given an initial condition, then no matter how many times you iterate forward or backward, you will not be able to arrive at a satisfactory solution. Okay? And you will find that if you try to find the mean of the time series and so on, okay, that mean will not be constant. So in order to induce stationarity or to make sure that the time series is stationary, we had imposed a certain restriction. Yeah. So in this part, we had imposed a certain restriction. Okay. You found that the solution depends on time. Okay. And this term will tend to 0 as m tends to infinity if we impose this restriction that alpha or a1 is lesser than 1. Okay. So that was the restriction. This should be a1. Just make the correction in your notes again. Okay, so we had imposed this restriction, and if this is the case, and as m tends to infinity or the sample size keeps growing larger and larger, we found that even this infinite sum over here, that will converge to 1 by 1 minus a1. So finally, we can write the solution to this first order difference equation this way. If we impose this restriction that a1 is less than 1, okay, the absolute value of a1 is less than 1, then we had said that this is not a unique solution, because for any arbitrary value of a, this will hold true, equation A. And then we solved for a by imposing a certain initial condition again, and we found out the general solution for this first order difference equation, okay, which takes this form. The form given in 10, if you simplify it to 11, you get this solution, which is identical to the previous solution that we had discussed. Okay. So this is where we had stopped in the previous class. I've shared the notes with you all already. I hope you all have had the opportunity to go through that. Have you all been able to take a look at the notes? Do you all have any doubts or questions from the previous class? Okay. Since nobody is saying anything, we'll just proceed with today's class. Okay, and yesterday was an official holiday for the institute. That's the reason that I did not take the class yesterday. But I found that some people have actually tried to join the meet. Okay, so the reason for not conducting yesterday's class was because it was an official holiday. If I ever need to conduct a class on a holiday, then I'll communicate with you all, and if it's agreeable to you all, only then we'll go ahead and set up a class and have a class on that day. Okay, so let's begin today's class. Okay. We are beginning with the stationarity restrictions for an Ar1 process. So if you remember the conditions for stationarity, they are that the mean should be constant and finite, the variance should be constant and finite again, and that the autocovariances should not depend on the actual point of time at which the autocovariances were calculated. Instead, it should only depend on the lag or the difference in time between the two values of the time series. Okay. So let's look at the stationarity restrictions for an AR1 process. So this is the first order autoregressive process or AR1 process, where we are assuming that this error term is a white noise process. Okay. And we found from our discussion in the previous class that the general solution to this first order difference equation has this form. Okay. If we impose the initial condition, then we'll have this form for the general solution of the first order difference equation. Now, if you try to find the mean of this time series, okay, so if we take expectation yt, you'll find that you end up with the equation 3. Okay. This is because this is a white noise process, so expectation et minus 1 and so on is equal to 0. Okay. So that term vanishes. So expectation yt is equal to this, equation 3. Now, if you find expectation yt plus s, okay, s periods into the future, then you will find that that is equal to this. But if you notice this term here, okay, here you have only a1t raised to the power t. Here you have a1 raised to the power t plus s. Okay. So the mean here of this time series is clearly not constant, or it is not independent of time. So you'll find that it depends on time, okay, on the basis of equations 3 and 4. So in order to induce stationarity, we assume that a1 is less than 1, that the absolute value of a1 is less than 1. Okay? And if t tends to infinity, okay, as our sample grows larger and larger, then this term, okay, which is again an infinite sum, you'll find that it converges to this term, a0 by 1 minus a1. Okay, so let's assume that t tends to infinity and that the absolute value of a1 is less than 1. So in the limit, yt will be equal to this, okay, because this term here, if you look at equation 2, as t tends to infinity, in equation 2, you will find that this term becomes smaller and smaller and eventually it vanishes, okay, because we are assuming that the absolute value of a1 is less than 1. So we end up with this form of the solution if we assume that the absolute value of a1 is less than 1. So now if we take expectations of this, you'll find that expectation yt is equal to some constant. Okay, remember that we've assumed that a0 is some constant, a1 is also some constant, okay, and the absolute value of a1 is less than 1. So expectation yt is now equal to some constant, okay, let's call it mu. And this holds true for all time. Okay. So even if you take expectation yt plus s, okay, you'll find that this term no longer exists. It simply vanishes. So you'll be left with only this term, okay, which I'm circling with my cursor. So the expectation of yt, or the mean value of yt, is some constant. It is finite. Okay. So the first condition for stationarity is satisfied. Now, if we look at the second condition, is this time series variance stationary? Okay, only variance, not autocovariance. So, if we look at the variance of this series again, okay, you will find that yt minus mu is nothing but this term, right? Sorry, this term. Okay, since this is the mean, you subtract the mean from this, you're only left with this term, okay, which is the summation of the errors. Now, if you take the expectation of that, okay, since expectation et minus 1, et minus 2, and so on is equal to 0, okay, you will find here that we are simply left with this. Okay. So if you find the variance of this time series now, you'll find that it's equal to expectation et square. Okay. Then a1 square et minus 1 the whole square, expectation of et minus 1 the whole square, okay, and so on. Okay, this term is over here. This is a1 to the power 1. Okay. So if you keep finding out this way, what is the variance? If you add up these individual terms, what you will find is that expectation et, because of our assumptions again, Okay, expectation Et is equal to sigma square. Expectation Et minus 1 is also equal to sigma square. Okay, and here you will find A1 square here. Okay. Now similarly, this will become A1 square whole square, so it becomes A1 to the power 4 and so on. Okay, so if you bring out all the common terms, which is sigma square, this is what you're left with in brackets. Okay. Now this again is some sort of an infinite sum which converges to 1 by 1 minus A1 the whole square. Okay. So this gives you the variance of this time series Yt, the first order autoregressive process Yt. Now if you look at the variance again, okay, this is some constant. Okay. Again, we assume that the variance of the white noise error term, it is finite and constant. Okay. So sigma square is some finite constant value. A1 again is some constant. So the variance is finite and constant. Okay. So the second condition for stationarity has been satisfied. Okay. Now let's look at the third condition. Is this time series covariance stationary? Okay. So here if you take expectation of Yt minus mu and Yt minus Yt minus s minus mu. Okay, so you're finding out the covariance between Yt and Yt minus s here. Okay. So now if you find out what the value of this expression is, okay, we are writing the two expressions here in brackets. Now if you simplify and find out what the value of this expression is, you'll end up with this term. Okay, remember that this again is that infinite sum which converges to this 1 by 1 minus A1 square. Okay, and if you simplify, you'll find that this is the common term which you're left with after simplification, sigma square A1 to the power s. Okay, where s is the particular lag that you have chosen to calculate the autocovariance. I'll just give you a moment to go through this, okay, in case you're worried about how we ended up with this form, okay, after going through the derivation. This is similar to what we discussed for the wall decomposition.
So ma'am, basically the covariance condition is that it's a constant number, right, for all terms.
Uh, See, here for covariance, what is important is that covariance should not depend on time itself. Instead, it should only depend on the lag which has been used to calculate the covariance. And you can see that the lag is appearing here, okay, as the power of A1. I'm circling this term. So you can see that the covariance depends only on the lag. Okay. For example, if you're taken Yt minus 1, okay, this term here would have been 1 raised to the power 1, A1 raised to the power 1. If it was 2, similarly, it would have been A1 raised to the power 2. Okay. So
All
it
right.
depends
So
only.
the takeaway is that our covariance condition is that it is not changing with respect to time. It
Yeah.
only depends on the number of lags and
Yes.
coefficients.
Yeah. Okay. So if you remember the wall decomposition that we had discussed, I had made you all write out the notation. Okay. We had taken a particular example, t is equal to 5 and the lag is equal to 2. Okay. So if you remember that, if you follow the same procedure here, okay, would you all like to do it now? If you follow the same procedure here, you'll end up with equation number 7. Okay. The last term that I've written here. Would you like a couple of minutes to do that for yourselves? Yes or no? Would you all like to just
Uh,
spend 2-3 minutes doing this derivation?
Ma'am, I think we will just take down what's on the notebook for right now.
Okay, fine. If anyone has any doubts about how we arrived at this particular form, then I just suggest that you take specific values of t and s and then calculate what the covariance will be. You will find that this is the final result. Okay. Since we have already discussed it in the context of the wall decomposition, I will not do it again for y'all. Okay. So y'all can refer to that. I've already circulated that particular page, or y'all can work it out for yourselves. Okay. So we'll move on to the next part. So here you can see that all the conditions for stationarity have been satisfied by this Ar1 process. Once we impose the restriction that the absolute value of A1 is less than 1. Okay. So here the mean is finite and constant. The variance is also finite constant. and the covariance depends only on the lag. Okay, it is not dependent on time itself, the particular point of time which was used to calculate the autocovariance. So here we can see that this Ar1 process, with the restriction that the absolute value of A1 is less than 1, is covariance stationary. Okay? So we say that it is a weakly stationary process because it satisfies these conditions. And in general, for all our empirical work, whenever we are doing practicals and so on, or if anyone in general is talking about a time series being stationary, you can be sure that they're talking about weak stationarity, okay, which satisfies all these conditions. Now in this context, I had shown you all a particular Excel sheet. Let's quickly take a look at that. So that might help you understand certain aspects of what we are discussing here. Okay, so in this sheet, what we are doing is looking at different AR1 processes. Okay, and what I've done is generated a series of random numbers, okay, to take the place of the errors, the white noise errors in our time series, okay, which form a part of the first order difference equation. So I've generated these random numbers using certain conditions, like the mean has to be equal to 0, okay, of this particular time series, and the variance is some constant. Okay, now I've saved the numbers because otherwise this keeps changing. Okay, right now in this it's not changing, but otherwise if you leave it as it is, it keeps changing. So I saved this particular set of white noise errors. So I generated about 100 white noise errors this way, okay, with a mean of 0 and some constant variance. Then after that, I constructed this AR1 process. Okay, you can see the equation for this AR1 process. A1 is equal to 0.9 here. Okay, so the absolute value of A1 is less than 1. Okay, this ET is basically the white noise error term that we are using. Okay, now this column here, I've numbered the column, I've given the columns headings so that you will find it easier to follow this time. Okay. Now in this column, okay, I've chosen an initial value of y naught is equal to 1. Okay, and then we begin constructing the time series from there. Okay, so y naught is equal to 1, and then we begin from that initial condition. Now this column here, it's just a1 raised to the power t. Okay, so t takes all these values 0, 1, and so on. Okay. So a1 raised to the power t is nothing but 0.9 raised to the power t. So now let's just plot this and look at what the time series itself will look like. Okay. So now if you look at it, it's clearly labeled here in this graph. Okay. So the blue line captures the AR1 process itself. Okay. And the red line here, it captures this term, okay, a1 raised to the power t. Okay, so you can see that for the initial first few values of t, you will find that this term dominates the time series. Okay, it follows this time series very closely, so you can say that it dominates the time series. But as time progresses, you will find that the value of the remaining terms, okay, which form part of the solution for this particular first order difference equation, those terms will begin to dominate the time series. Okay? So somebody had asked me in the previous class whether it forms part of the solution. That's right. It forms part of the solution when you're considering the general solution for the time series. Okay? So you'll find that the errors, if you look at the general solution, the errors are raised to the, are multiplied by this coefficient a1 raised to the power t. Okay. Also, if you look at the initial value of y naught, okay, y naught is also multiplied by a1 raised to the power t. So that is how this term pops up in the general solution for the first order difference equation. So you'll find that for the first few values, this term dominates. But as time progresses, because we have assumed that the absolute value of a1 is less than 1, which is true for the particular equation that we're looking at, okay, so the influence of this term begins to fade away. Okay, and you can see gradual convergence to 0 here
Ma'am,
for this particular time series. Yes?
ma'am, could you also plot column C white noise errors along with these two
Okay,
in the
yeah,
same graph?
all right. So you can see these white noise errors. Okay, here the blue line captures the white noise errors. Okay, you can see that they're clearly stationary. The mean more or less fluctuates around the value of 0, right? You can see that the mean is more or less 0. Even the variance is more or less constant. Okay, you can see that in the time series for the white noise errors. Now, if you look at the other two parts, okay, what you will see that is that gradual convergence is taking place. If you remember the discussion from the previous class also, okay, we had found that if the absolute value of a particular term, in this case a1 and b are the same, okay, they have the same value. So if the absolute value of that particular term is less than 1, then convergence takes place, okay. And if the absolute value is positive, sorry, if a1 is positive, then you will find that convergence is direct, otherwise it will be oscillatory, okay, if a1 is negative. So the same thing is seen over here. You'll see that convergence is more or less direct. It's taking place directly because A1 is positive here. Now, as time progresses, you'll find that even the influence of the errors gradually begins to diminish. Okay, on this particular time series. I don't know if you're able to see that. Okay, but generally, because the error terms are multiplied by a1 raised to the power t. Okay, so even that influence will gradually begin to diminish, and you will see gradual convergence taking place. Okay. Now let's look at another time series. Do you all still want me to plot the errors? It will look the same. Okay. Since we are
Ma'am, why,
using,
ma'am, why did you say that the error terms will be multiplied by
uh,
a
can,
raised to power t?
I'm sorry, I'm not able to hear you properly. Can you just speak a little louder?
Ma'am, the white noise errors will also be multiplied by a raised to power t.
Yeah, so that's why I said the influence of those errors will gradually begin to diminish. Okay, so in any time series, if you remember our discussion and what we were saying when we were discussing the wall decomposition, the side J's are the weights, okay, associated with the error terms, and you'll find that errors in the distant past have a lesser weight compared to the errors in the more recent past. Okay, so the same thing happens here. So you'll find that past discrepancies, okay, or errors will have a lesser impact on the time series, and that's why you see the gradual convergence. Instead, if the errors were only having a larger and larger influence on the time series, you will not see convergence taking place. Is that all right?
Yes, ma'am.
Okay. We'll see that in the next couple of equations that I've prepared. Okay. So let's look quickly at this one, and I want you all to tell me, if possible, what is happening here. Okay. You all can see this, right? Can anyone tell me what is happening, what we are seeing?
The value drops really fast as compared to the previous one.
Yeah. Okay. So basically, convergence is taking place much faster here. What do you think is the reason for that?
Could you repeat the question, please? I'm so sorry.
You said that the value drops very fast here, right? Okay,
Yes, ma'am.
that's what you said. So I'm asking you, why does it happen? Basically, when you're saying the
Ma'am,
value drops,
because of the a1 value,
yeah,
because we can see that every consequent figure, not figure, I'm so sorry, number
hmm,
will be approximately half of the previous one, and in the line before us it was 0.9 times. So
yeah,
we can see that out here it will drop a lot faster, but
yeah,
at the end of the day, once you keep on dropping, then where does it tend to will depend on the sum of the GP. So that is where it might plateau.
Okay. Yeah, so basically you're right here. Okay, so what you're saying is that here, because of the difference in the value of A1, we see a slightly faster convergence taking place. Okay, so when you're saying that the value is dropping, basically the time series is converging to this value of 0 quite rapidly compared to the previous AR1 process. Okay, and that is all because of the value of A1 here, which is 0.5, okay, which is smaller compared to this. Okay, so you said approximately half, so that's right. Okay, so here you can see that because A1 is raised to the power t, okay, and A1 here is smaller. Okay, so gradually the effect of the previous errors will begin to diminish much faster compared to this time series. Okay? So you'll find that the discrepancies that are there, okay, that will begin to diminish quite fast. Okay? Also, if you look at the A1T Y0 term, okay, the influence of the initial value will also drop quite quickly. Okay, so you'll see that there's a rapid drop from the initial value of 1, it drops rapidly to 0 quite quickly. Okay, so you'll find that even the initial value has a lesser influence, all because the magnitude of A1 is much smaller here. Okay, so if A1 is smaller, then you'll find that the rate of convergence is faster. Okay, so that is the point that I was trying to make here. Okay, the rest of the logic is similar, okay, what we were discussing in the previous situation. Okay, now anyone can answer the question again. Just describe what you're seeing and why you're seeing it.
The value is oscillating since A is negative.
Yeah, okay. So since A1 is negative here, you can see that the value of this time series is basically oscillating, but again, convergence is very rapid because of the smaller value of A1 compared to the first AR1 process that we were looking at. Okay. Now let's look at this one.
Just a question.
Yeah.
Will they always converge to 0, or can they converge to some other number also?
Yeah, some other number is also possible.
All
Here,
right.
here, if you look at the type of time series that I've constructed, A naught, which was your constant term when you write a general first order autoregressive process, we have the term A naught also, which is the constant term or intercept. Here I've assumed it's 0. Okay? So that's why it's converging to that mean of 0, basically. Now let's look at this one. Okay, can anyone tell me what is happening here?
Maybe we are getting a number which is centered around 1, and the white noise process is taking more of the weight than the AR process.
Okay, you're very close to the answer. Just think again. Now look at this equation. I'm circling it here. If I just write it in the first difference form, what will I get? Anyone can answer again.
Ma'am, I think it'll go to 0, the difference.
No, just use the equation itself. If I write this in the first order form, what will it be? Yt minus 1 is equal to Et. Okay, so the change in Yt, okay, from period t minus 1 to t basically is equal to the error term and time t. Okay, are you able to follow that? Would you like me to type it?
No, ma'am. Are you trying to say that it's only the white noise process which survives after writing this?
No, what I'm trying to say is that the changes in yt will simply be equal to et, which is the error term at time t. Okay? So if you're looking at how yt changes from one period to the next, the only thing that will tell you how it's going to change is the value which the error term takes. Okay? Just think about it a little bit. Okay? What I want you to do after the class, don't do it right now. Just write this equation and include an intercept term. Okay? Just write an equation, Ar1 equation, where you have an intercept term A0, okay, and A1 is equal to 1, and then follow that iterative process and see what solution you have for this particular Ar1 process. Okay, do it after the class, not during. I'll just repeat it so that all of you can do it. Just write out an Ar1 equation where you have the constant term or intercept term included, okay, which is A0, and then you have A1 is equal to 1. Okay, and then find the solution for this first order difference equation and see what you get. Okay, by using that process of iteration. Do this at the end of the class, okay, or later on, whenever. And in the next class, we'll try and discuss that. Okay? But basically, once you are able to do that, what you will see is that the changes in yt, okay, if I take yt minus 1 this side to the left hand side, what I'll get is yt minus 1, which is nothing but delta yt, okay, that will be equal to et. So the changes in yt from one time period to the other are only captured by the error term. Okay, so it becomes very difficult to predict what is the value of yt from one period to the next. Okay? So this process is called a white noise process. Sorry, not white noise process. It's called a random walk. Okay. So the name comes from the fact that if you watch a drunkard walking around, okay, after he's drunk and he's walking around, you'll generally find that he is not able to walk in a straight line. Okay, the pattern of his walk, if you try and trace it, it will be more or less like a zigzag. It will be meandering all over the place. Okay? So this process, which has A1 equal to 1, okay, is called a random walk process, and we'll study it a little later on. Okay? So basically the point that I'm trying to make here is that you will not see convergence to the mean value of 0 here, okay, in this sort of a process. Now let's move on to the next one. Again, try and describe what you're seeing. Okay, you're not able to see the blue line, but it's there. Okay, if I just delete this, then you'll get it.
Instead of it converging, it is now diverging from left to right.
Yeah. Okay, so here you can see divergence. Why is that taking place?
Ma'am, because again of the 1.2 factor.
Yeah.
So what is happening is that every time it is increasing by a bit and bit, but the thing is that once it reaches a certain point, it's become so big that it just gets out of hand.
Yeah. Okay, so basically you can say that the time series in some case it's going to become larger and larger. Okay, and the error terms also, since they're going to be multiplied by this coefficient a1 raised to the power t, okay, you'll find that the effect of the discrepancies also becomes larger and larger. Okay? In this particular graph, okay, what you're seeing is, it's not visible to you all, this blue line here, okay, but it looks like it's overlapping, but this is not the case. If I show you the actual values between of these two, you'll find that there's always a difference between the two. Okay, if you look at the successive numbers, you'll find that there's always a small difference between the two. Okay? So convergence doesn't actually take place. Okay, even though it might look like the two series are overlapping, you can clearly see that there's divergence. Okay, and even between the two series, they'll never actually be equal to each other. Okay, so I've taken only 100 observations. That's why you might be seeing that sort of overlap. If I take a much larger sample size, then you'll probably see that the two lines are diverging from each other. Okay. Now again, the last one is, since you'll have answered the other questions, okay, here you can see that there's divergence again. Okay, although it looks like initially there's convergence, but later on you'll find that there's divergence. Okay, and you can see that the oscillation is because of the negative value of A1 here. Okay. Again, it looks like there's some overlap, but if you take larger number of observations, you'll find that there is some discrepancy between the two lines. Okay, so I hope why A1 is so important. Okay, the magnitude of A1, why is it so important? What does it mean for an AR1 process? I hope it was clear by looking at all these time series that we have constructed. Okay, so today what we'll do is we'll move on. The stationarity part was something that I shared from the previous class. Okay, so today we'll try and solve that AR1 equation itself, the first order difference equation, in a slightly different way. Okay, so before we do that, in a much simpler way, because once we move on to higher order processes, okay, for example, if you move on to AR2, it's still simple. Okay, if you have to solve the difference equation, find the complementary function, then the particular solution, and so on, it will still be simple. But suppose you have an ARP process, okay, where P is equal to 10 or 5 or something like that, it will become more and more complicated for you to solve the difference equation by using the methods that we have discussed so far. Okay, it will become very complex because there will be a lot of algebraic terms in your equations. So generally we use something known as the lag operator to find a far simpler solution and quicker solution. Okay, so before we solve that first order difference equation, let's understand what is the use of the lag operator, how it is used in time series econometrics. So if you take any time series xt, okay, then if I write lxt, where L is the lag operator. Okay. So if I write lxt, it simply means that I'm lagging xt by one period. Okay. So it gives me xt minus 1. Now, if I write lxt minus 1, again I'm lagging xt minus 1 by one period. Okay. So you can also write this equation this way, L into lxt. Okay. So it becomes L square xt, which is nothing but xt minus 2. Okay. So you're just lagging xt by 2 periods here. Okay. Similarly, L raised to the power k xt will mean you're taking k lags of this particular time series. Okay. Now, if k is equal to 0, okay, then you simply get xt. You're not using any lags at all. Okay, now, if k assumes a positive value, okay, when you're using this subscript or power k, okay, if it assumes a positive value, that means you're using lags. Okay, so xt will be lagged by k periods. Now, if k assumes a negative value, it means that you're looking for leads or you're trying to use leads. So you'll be leading xt by k periods here. Okay, so you'll be looking at xt plus k. Okay, so one particular example of this is given. If I'm raising L to the power minus 3, okay, it's nothing but xt plus 3. Okay, so I'm taking a lead here. If you want to understand it, again, if you're simply looking at the fact that this is a lag operator, so why am I getting this result? Okay, if you take xt minus of minus 3, you'll get the same result. Okay, I hope this was clear to all of you. So generally we use these lag operators to simplify finding the solution to a difference equation and so on. Okay. Now there are certain rules.
Ma'am,
Yes.
is this just like a form of nomenclature?
Yeah, it's a method to denote that you're taking lags. Okay, that's why it's called the lag operator. it's basically a symbol that you show that shows that you're performing this particular operation of lagging a variable. Okay. So now there are certain rules which apply to these lag operators. For example, this rule. Okay. You'll find that there are similar rules which apply to exponents or powers. Okay. So if I'll allow you to read it, it's too much if I try to read it myself. Okay. But basically, if you have two lag operators, one raised to the power n, the other raised to the power m, you'll simply be lagging xt by m plus n. Okay. Now the first difference of xt can be written this way. Okay. xt minus 1. Okay. So if you write it this way, then it simply means that you're using the first difference form of xt. Okay. This is nothing but this. Okay. So we might be using this subsequently when we are discussing certain derivations. So it will be helpful if you become familiar with these. Okay. Similarly, if you take the fourth difference, okay, this is nothing but xt minus 4. So you can denote it this way using the lag operator. Now, suppose I have xt and its first three lags, okay, and I want to take an average. This is done for addressing issues of seasonality and so on. Okay, so if I want to take the average value of these variables, then I can denote this same equation this way. Okay. Now, in general, if you have an AR2 process, okay, instead of writing out the entire equation, okay, like we do here, okay, it will be far simpler to simply use the lag operator. So we use this notation for this. Okay. Since there will be p autoregressive coefficients, we put AP here, okay, and this is the lag operator. So this means that there are p autoregressive coefficients and you'll be taking p lags of this time series xt. Okay, this will give you xt minus 1, a1 xt minus 1. This will give you a2 xt minus 2 and so on. This will be ap xt minus p. Okay, this is simple, right? I hope you all are able to understand this. Okay, then some other rules which apply to these lag operators. Okay, one is that the lag of a constant is that constant itself. Okay, if you assume that delta is some constant here, then the lag of any constant will always be that constant itself. Then the distributive law applies to lag operators. Okay.
Ma'am, can you please slow down with the rules?
Yeah. I will be sharing this, so you need not copy the whole thing. Okay, just let me know once you've reached point 3.
Yes, ma'am, it's done. Ma'am, just wanted to ask, in the where equation 7 is mentioned on this notebook, you've written AP, then you've written bracket L xt. So that L is like, are you writing it as a denotation or are you using that as a? I'm not understanding. Like I understand what L is. It's just like a way of notation, but
See, when I'm writing this, if you look at only at this part, it is denoting that you'll be taking the lags of xt. Okay. Now, when you're taking the lags, okay, they'll be multiplied by these autoregressive coefficients. So this term is indicating that there are p such autoregressive coefficients. Now, if p is equal to 2, you will have a second order autoregressive process where there will be xt and 2 lags of xt. Okay, so this whole notation, this is all just notation. Okay, you're trying to say that this particular equation will have xt itself, okay, and 2 lags of xt. If I take p is equal to 2, okay, if it's only given p, then I'll be taking p lags of xt. So now p will run from, you can say in this particular equation, it will run from 0, 1, 2 and so on, okay, up to p. So when L is raised to the power 0, it's simply 1, right? Okay. And A naught, you'll have A naught. So we generally assume that A naught is equal to 1. So you'll have simply xt minus the next term will come in, okay? So you can think of it that way. I hope this was clear to you. Okay, now we'll move on to the next part. Okay, if you now look at this fourth point over here, okay, AL in brackets and delta. Okay, now delta is that constant that we were talking about here. Okay, so if I'm taking lags of a constant, okay, it will be equal to that constant itself. Now assume that I'm going to take p lags of that constant. Okay, it might seem very silly to denote it this way, but this will be useful a little later on. Okay, so if I'm taking p lags of the constant, then I can denote it this way. Okay, so I'll have 1 minus, just like how you had it over here. Okay, 1 minus a1 minus a2 and so on up to ap, okay, into that constant delta. Okay, so this, we are using the lag operator here for the constant, and we are using this term to denote that we are going to take lags of this constant. Okay. Now in general, since we denote AR models where the number of lags are not specified, we generally denote it by ARP. Okay. So that's why we've simply used this term here. So it will be understood that it's an ARP model, okay, where you'll be taking p lags of this constant. Okay, then what I said earlier, if L is equal to, if L is raised to the power 0, it's equal to 1. Okay. Then to denote this particular term in brackets here, okay, we simply use this term at times, A1. Okay. It's simply used to denote this term which you see in brackets. Some of this notation we will be using, some we will not be using. Okay, so don't worry about it. I'll be circulating this later.
Ma'am, can we say that capital A was equal to the value of that bracket? Because I did not get the fourth rule.
Yeah.
Okay.
Then rules of lag operators. Okay, again, if you look at the sixth rule, if we assume that the A is here, absolute value of A is less than 1. Okay. In general, we are still talking about A1. Okay, so if the absolute value of A is less than 1, here you can write this same equation this way. Okay. This infinite sum converges to this. This is something that we saw when we are solving the first order difference equation itself. Okay, so this infinite sum here will simply converge to 1 minus AL. Okay. Now for A greater than 1, there are proofs for this, okay, but we won't be getting into that. If you are interested, I'll share the proofs later on. Okay. For A greater than 1, okay, this infinite sum, it converges to this. Okay. And we can write this term here, yt by 1 minus al. You can also write it this way. This is not so important for us, okay, so don't worry too much about it if you're not able to understand it right now. Okay, so let's just see the use of the lag operators itself, how we are going to use it. Okay, so if you have an ARP process, instead of writing out all these terms, okay, we can denote the same process this way, where you shift all the yt terms this side to the left hand side, So then you get yt minus a1, yt minus 1 and so on. Okay, all these terms are on the left hand side. Now instead of using that itself, we use the lag operator, and we can write the autoregressive coefficients and the lag operator this way. So on the right hand side, you'll only be left with this intercept term and the error term. Okay. Or we can also denote this way, where A again denotes this term in the brackets, and you have the lag operator. Now you can also have, so far we've been discussing only autoregressive processes, but suppose you have an autoregressive and moving average process. Okay, so somebody was asking about this in the previous class. So a moving average process is basically some kind of a sum of these white noise error terms, okay, where each error term will be multiplied by a particular coefficient beta I. So here we are taking Q lags of these error terms. So that's why the MA part or the moving average part of this equation has Q lags. Okay? And the AR part, where since we are talking about auto regression, YT is being regressed on its own lags or own past values. So that constitutes the auto regressive part. So there you have P lags of YT being involved, and you have Q lags of the error term itself. Okay, so this becomes an ARMA process, okay, autoregressive moving average process, okay, which is denoted by ARMA PQ. Later on, we'll be studying ARIMA PQ also, where you have ARIMA, okay, that is ARIMA PQ. So the I there stands for integrated. So if you have a time series which is not stationary, then we'll call that particular time series which has both these autoregressive and moving average elements, but it is not stationary. It's called an ARIMA process, where depending on the lags again, the general notation is ARIMA PQ, okay, process or model. So here we can denote this ARMA PQ model again using the lag operators in a very simple way. Okay? So this will tell you about what are the lags of YT which are involved. Okay? So in general, again, this term is denoting that there will be P lags of the YT process. And here again, we are not specified, but in general, it is assumed that there will be Q lags. Okay? Where if Q assumes specific values, then you will be able to know what is the lag order. Okay? So the moving average terms, there will be Q lags of these error terms. Okay? So for the error terms, we use BL, okay? Where this operator is nothing but 1 plus B1, okay? Plus B2 and so on up to BQ, beta Q, sorry. So these are two lag operators which are used. This is for the autoregressive terms. This will be for the moving average terms. So it just helps us to simplify the notation so that you don't have to write such big equations. Okay. So AL and BL are polynomials of order P and Q respectively. Okay. So this denotes the autoregressive part, and this the moving average part. Do you all have any doubts so far? Any questions or doubts?
Ma'am, I have a question regarding the random walk.
Yes.
So, ma'am, when there is a possibility where our y variable can only take the values +1 or -1, how would we that would be used? How would we use that in random walk? Like, how would we solve a problem in random?
See, it is not the y variable itself which is assuming the value of -1 and +1. That's what you said?
Basically, it's a dummy variable, so it's a logistic thing, and we are trying to.
See, dummy variable is completely different. Dummy variable will assume a value of 0 in particular cases and 0 when those cases, value of 1 in a particular context, 0 otherwise.
Categorical variable. So if we have like put give a -1 to certain situation and 1 to certain situation,
Hmm.
then how will be the random walk would be different from the normal thing that we have seen just now?
See, one thing, let me make it clear. Random walk is the case where A1 is equal to +1. Okay, not -1. So we are saying that A1 is equal to 1 only, +1. Okay, then you see a random walk where the change in yt or a particular time series is equal to the error term. So you will find it hard to predict subsequent values of that particular time series. It will not be easy to predict what will be the next value of yt in the next time period because it's equal to some error term which is some random variable.
Okay, ma'am.
We'll be discussing this a little later once we are discussing stationarity and all that. So it will come in there again. Okay? Till then, if you still have some doubts, just note it down. So when I'm discussing that part, you can ask me again.
Okay, ma'am. Thank you.
Ma'am, can you move a little bit up on the sixth rule?
Yeah.
Ma'am, I'm not able to understand in this use of lag operators, how is this second equation giving us the first equation?
Which
Like
second?
1 minus E1L minus E2L square, or
Hmm.
this whole thing in bracket multiplied by YT.
Hmm.
How is this equation giving us the equation which is just above it?
This one. Let me point my cursor. You're talking about 7 and 6, is it?
No, ma'am. This use of lag operators or heading.
Okay. Wait. Let me go up. Yeah.
Ma'am, it's in the niche only.
Okay. This part.
Ma'am,
Somewhere here.
after rule 6 and 7, there is this heading use of lag operators. I'm talking about that.
Oh, okay. Okay, yeah.
Yeah, I'm talking about this second equation which is written on use of lag operators, or this 1 minus E1L minus A2L square, which is a whole in bracket. How is this equation giving us the equation which is just above it?
Okay. See, take this equation. I'm pointing at it. Okay, the first equation. Now, can you tell me what sort of process you're looking at?
Ma'am, actually, I was trying to
No,
call
just no. I understood your point. Just tell me what you're looking at. What sort of process is it?
ARP process.
Yeah, it's an ARP process with P lags of YT, right? Okay, now from this equation, just take all these YT terms to the left hand side.
Yeah, ma'am. Okay, got it. Yeah,
You understood?
got it. Yeah, thank you.
Okay. Any other doubts? Let's just take a quick 5-minute break. Okay, it's 3:32. We'll meet at 3:37. I'm leaving this page in case anyone wants to copy it. Okay. So we'll meet at 3:37. Okay. Okay, I hope you all are back. It's 3:37, so we'll continue with the class. Okay, so let's solve that same AR1, the first order difference equation using the lag operator. You will see how much simpler it is, okay, and why it's used especially for higher order autoregressive processes. So this is slightly blurred, but I hope you're able to see it. Okay, so this is the AR1 process. Now again, we just shift this yt minus 1 term to the left hand side. Yeah, and then we'll begin using the lag operator. Okay, so using the lag operator, we can write 1 minus a1l yt is equal to this. Okay, so yt is nothing but this. Okay. So this is a much simpler solution. We don't have to do any sort of iteration, assuming initial conditions, any of those things. Okay, so the long-winded derivation that we did in the previous class, okay, it's simplified to just 2-3 steps using lag operators. Okay, you can see how much simpler this is. So this term here, 1 by 1 minus a1l, okay, it's nothing but this infinite sum. So if you remember the solution that we wrote when we were using the iterative method and so on, you would have found this term is there. Okay? A naught is multiplied by this infinite sum, A1, A1 square and so on. Okay? So the same thing has been written using lag operators. So as t tends to infinity, you will find that this converges, this infinite sum, it simply converges to this. Okay, so this is what we've written in equation 2. The same applies here. Okay. So I've just written that same thing over here. Okay. A naught multiplied by that same infinite sum. Okay. It just reduces to this. So this is just an alternate method of writing the same thing. Okay. Equation 2 and equation 3 are basically telling you the same thing. So as you can see, it is much simpler to solve difference equations using this sort of methodology where you're using lag operators. Okay, so even for higher order processes, instead of carrying out that whole iterative process, we'll simply be using the lag operator and then solving the difference equation. I hope this was clear to you all.
Ma'am, can you show that page again?
Yeah.
Just 1 minute.
Ma'am, that third equation, the last thing, that summation I is equal to 0 to infinity ai1. Could you explain that bit, how that comes from the equation from above? We have taken e t common.
Yeah.
And then
so somebody needs to mute themselves. Okay. Somebody, I can hear the background noise. Yeah. So here, if you remember the iterative process where you were substituting, okay, y1 is equal to a naught plus a1 y naught plus e1 and all those things. So in each successive, go back to your notes from the previous class. Okay. So in each successive stage, you would have found that you are collecting those error terms, okay, et plus a1, et minus 1 and so on. Okay. So as you were solving the difference equation, you ended up with this term. Okay, so if you look at the values, okay, if I put I is equal to 0, so this will simply be et, the first term will simply be et. If I is equal to 1, then I'll get a1 et minus 1. Okay, so this is just the sum of those terms. So I'll keep getting et plus a1 et minus 1 plus a2 et minus a1 square et minus 2 and so on. Okay. So I'll keep getting these terms where these autoregressive coefficients are raised to the power I, okay, at each, whatever value of I you put from 0, 1, 2 and so on, keep doing that, okay, up to infinity. So you'll keep collecting these autoregressive terms where they're multiplied by the you'll be collecting the error terms where they are multiplied by these autoregressive coefficients. Okay, so you'll get et plus a1 et minus 1 plus a1 square et minus 2 and so on. So that whole thing is captured by this. Now this is nothing but this infinite summation. Okay, if I'm writing this here, if you look at this, this gives me ET 1 and 2 ET. Okay, then this gives me A1 ET minus 1. Okay, then A1 square ET minus 2. Okay,
What
just
about
follow
the
the
lag
yeah,
portion
that's
of
what I'm
this?
talking about. This lag part, it's telling you how to lag the error terms. So if I multiply this, just follow my cursor. Okay, if I multiply this, I get ET. Then if I multiply this, I get A1. Since it's only L, I'll get ET minus 1. Then
Okay, got
here,
it, ma'am, got it.
yeah.
I
So
mean, the
this,
first for the first time, it will be A0 upon 1 minus A1 L will be there, right? Not just A1.
A0, which one are you talking about?
Ma'am, in this third equation only, when
Yeah.
you'll see the first term, it's A0, 1 minus upon A0 upon 1 minus A1. Instead of 1 minus A1, it should be 1 minus A1 L, right?
No, since here I'm not using the lag operators. Okay, so I just get 1 minus A1. Go back to your notes from the previous class. Let me just show you if it's there here. Okay, this was the solution to the difference equation. That same thing I'm showing you here. If you're using that iterative method without lag operators, you're coming up with this. See, basically here A1 is some constant. Okay, that is our assumption. A1 is some constant. So lag of a constant, if you apply the rules of lag operators, lag of a constant is that constant itself.
Okay, ma'am. Okay.
Got it? Okay. This infinite sum, it just converges to A naught by 1 minus A1. If you look at the previous derivations that we have done, that was the solution that you ended up with for the difference equation. Let me show you. Yeah, if you look at this part, okay, so here you have that, which then reduces to, if you assume that A is less than 1, A1 is less than 1, then you end up with this.
Ma'am, then why are we putting the lag thing over
Yeah.
here?
In
Because
equation 2, why L has been put it? I mean,
because
equation 2, A0 upon 1 minus A1 L. Here,
because
yeah.
see, because you're doing the derivation, right? How did you get this A1L? It was multiplied by this. So when you divide both sides by 1 minus A1L, this is the result that you end up with.
Okay, ma'am, got it. Just,
It's part of the
below the
derivation.
just below the second equation, you
Hmm.
wrote 1 upon 1 minus A1L is equal to this infinite series.
Yes,
So
that
write
is,
A naught into that infinite series would be 1 minus A1 by L now, because that's what we have defined above.
yes, which is what
In
I've
the third
written.
equation,
Wait,
it should
wait,
not be L.
just give me a moment. See, here this is using the lag operators. What I'm trying to show you is you will get the same result. Here I haven't used the lag operator if you look at this term.
The first term, not the second term, first
Yeah,
term.
I know. That's what I'm trying to tell you, that you're ending up with the same result whether you use uh, the method of lag operators or if you use the iterative method. Okay. In the iterative method, in the limit as t tends to infinity, the other term vanishes. Okay. We had used this. Okay. As t tends
A1
to,
L should be equal to A1 only because constant is there.
yeah. What I'm trying to tell you through this whole thing, this answer, equation 2 has come by using the lag operators. This is the same result that you got by using the iterative method. That's what I'm trying to show you here. Okay, it's not following directly from this. Because I've put this, I think you all are getting slightly confused. But this is basically the same thing. Since A1 is some constant, even if I put L here, okay, so this will just be 1 minus A1 because it is a constant. Okay, you can
Okay.
stop here. If you're getting confused, just stop here. What I'm trying to show you is you're getting the same results if you use both the methods, whether you use the method of lag operators or whether you use this method of iteration. I hope the person who had that question, you're convinced now, I hope.
Yeah,
Yeah,
ma'am,
ma'am, just trying to wrap my mind around it.
Okay, fine. Probably once I circulate the notes, you'll find it a little easier. But just remember that I'm only trying to show you that both the methods will yield the same conclusion or result.
Okay.
I'll just modify it slightly if you want, so that it's clear that I'm talking about that second method there. But even if you put L, since it's a constant, you will get the same result. Okay, so for higher order systems, okay, we can solve this way by using the lag operator itself. Okay, so instead of doing the cumbersome derivation using iteration and so on, okay, we can simply write, for example, an Ar2 process where you have two lags of yt. Okay. You can write it this way using the lag operator, okay, and then solve for yt. Okay, so this gives you the solution for this difference equation, second order difference equation. Okay. Now similarly, if you have an ARP process or model, again you can use the method of lag operators to solve for yt. Okay. So this becomes much simpler and faster compared to the other methods that we discussed in the previous class. Okay, I'm just giving you a minute. If you all have any questions or doubts, you can ask me. Okay, can I move to the next part?
Yes, ma'am.
We'll quickly look at the autocorrelation function for an AR1 process, and then we'll switch to another topic. Okay? So if you remember the autocorrelation function, okay, we had briefly mentioned this and we had discussed what is the formula for calculating the autocorrelation coefficient. Okay? This is very similar to the correlation coefficient, but here, since you're looking at the correlation between yt and its own past values, that's why the term autocorrelation is used. Okay? So for an AR1 process, if you remember the previous part of our discussion today, okay, this gives you the variance of this process. Okay? Variance of yt is given by this. Gamma 0 indicates the variance. Okay? This is the autocovariance between yt and yt. Okay? That's why it's the variance. So it was given by this formula. Now the autocovariance between yt and yt minus s, okay, again we discussed this today. It takes this form. Okay? So gamma s, which denotes the autocovariance between yt and yt minus s, is equal to this. Again, you will find that the variance is constant and finite, and the autocovariance does not depend on time, only on the lag, okay, between the two time periods. Now to find the autocorrelation coefficient, okay, this is the general method that we denote the autocorrelation coefficient by rho I, okay, where I takes values from 0, 1, 2, 3 and so on. Okay, so rho 0 is nothing but gamma 0 by gamma 0, okay, which is the variance by the variance is equal to 1. If you're trying to recall the function, it will just be autocovariance divided by variance. Okay. So here, since it's gamma 0 by gamma 0, rho 0, okay, or the autocorrelation coefficient at lag 0 will always be equal to 1. Now rho 1, okay, which is the autocorrelation coefficient between yt and yt minus 1. Okay, that is equal to gamma 1 by gamma 0. This is the general formula. Okay. For rho 2, it will be gamma 2 by gamma 0. Okay. Now gamma 1, if you just substitute here, since s is equal to 1. Okay. So wherever you find s, just substitute 1 here, since you're looking at rho s here, okay, where s is equal to 1. So you'll find, if you simplify this, the covariance by variance, okay, it's equal to A1. So rho 1 is equal to A1, then rho 2 similarly is equal to gamma 2 by gamma 0. Okay, since we are looking at rho s, okay, at lag s, the autocorrelation coefficient at lag s, where the lag is equal to 2. Okay, so here in the covariance formula, just put s is equal to 2. That's what you get here, divided by the variance again. So here you get A1 square. Okay. So similarly, you'll be able to calculate rho 3 and so on. So the general formula, if you look at the pattern that you're getting, is rho s is equal to gamma s by gamma 0. Autocovariance at lag s by variance, that is equal to A1 raised to the power s. Okay. So that particular lag which you're using to calculate the autocorrelation coefficient, for a first order autoregressive process, the general formula will be rho s is equal to A1 raised to the power s. Okay, just keep this in mind. You'll have been able to follow this.
Yes, ma'am.
Now, a necessary condition for stationarity for AR1, which we already saw, is that A1, the absolute value of A1 has to be less than 1. Only in that case will you get a constant and finite mean and variance and so on. Okay. So the ACF, okay, should converge to 0 geometrically if the series is stationary. Now, if you take these autocorrelation coefficients, okay, which you have calculated here, we usually ignore rho 0 usually, okay, since it's equal to 1, it's not very interesting for our purposes. So we generally look at rho 1 to rho s, okay, up to s lags. And what you need to do is take the autocorrelation coefficients and plot them against the lags. Okay. So you will be plotting each of these against the respective lags. Now,
Ma'am, autocorrelation coefficient will always lie between 0 and 1, right?
Between 0 and 1, yeah. Sorry, between -1 and +1. Okay. So similar to the correlation coefficient. Okay. Just like how you can have perfect positive correlation and perfect negative correlation. Since here you're
Since
looking at the
A1 is not supposed to be negative and should be less than 1, so how would that would come as a negative thing?
This one you're talking about, equation 4.
Ma'am, in the general formula, the seventh equation, PS is would be equal to A1 to the power of S.
Yeah.
If we are assuming that the mod value of A1 is less than 1, that means that positive value would be less than 1, right? And the positive to the power of something would be positive.
Yes.
So how would we get a negative, damped oscillatory path?
See, if A1 is, we are saying the
Okay, I got
absolute
it. I
value of
got my
A1 has to be,
mistake. Yeah, I found my mistake.
it can take negative values, but it has to
Yeah.
be less than 1, basically.
Yes.
So here, if you look at it, the ACF or the autocorrelation function is basically a time plot of the autocorrelation coefficients plotted against the respective lags. Okay. So this ACF, it should converge to 0 geometrically if the series is stationary. Okay. So since if you're looking at the values that you're getting here, A1, rho 1 is A1, rho 2 is A1 square, rho s is A1 raised to the power s. Okay, so you can see that there'll be some sort of a geometric decay. Okay. which takes place. As you raise A1 to higher and higher powers, you'll expect that the autocorrelation coefficient will become smaller and smaller. Okay, so the ACF for an AR1 process should converge to 0 geometrically if the series is stationary. Now, if A1 is positive, you will find that there is direct or non-oscillatory convergence. Okay? It's not the same as what we saw in the Excel sheet, but it will look similar. Okay, since there we were actually plotting the time series, not the autocorrelation coefficients, but the appearance will be somewhat similar. Okay? And A1, if it's negative, then you'll see oscillations. Okay, but they will dampen as the number of lags increases. So there'll be a damped oscillatory path around 0. So there'll be fluctuations, but they'll grow smaller and smaller around 0. Okay? So later on, I'll show you all some images of autocorrelation functions, okay, and then we'll discuss those. But in general, remember this, that for an AR1 process, the autocorrelation function has this sort of an appearance. If A1 is positive, then there'll be a geometric decay okay, towards 0, depending on what is the value of A1. Is it positive or negative? If it's positive, then you'll see direct decay. Otherwise, there'll be oscillatory decay. Okay, before we come to the next part, I just quickly wanted to go through something so that you'll understand some aspects which are related to stationarity. Okay, because if I don't cover it, then your course will be somewhat incomplete. Yeah. This is just for your understanding. You will not be asked questions about this. Okay? So we'll quickly just discuss what happens in higher order systems. Okay? So far in the previous class, we discussed how to solve a first order difference equation. And we said that the solution for that difference equations, for a first order difference equation, it will be composed of two parts. Okay? So the general solution will be divided into two parts. You will have one particular solution where you will be using the entire first order difference equation, and the other part will be the complementary function where you're moving all the yt terms together, okay, to the left hand side, then setting that equal to 0, and then you're solving. Okay? So for the first order system, if you remember, you'd have had abt minus 1, okay, raised to the power t minus 1. So there, once you solved for b, okay, the objective when you were doing that was to solve for b. 1 second. Okay, so this is what I was talking about. So when you're trying to find the complementary function, okay, which is one part of the general solution, what you were doing is using this method where yt plus 1 is equal to this abt plus 1, and then you have yt is equal to abt. Okay, you're setting these two equal to these two things, and then you solve for b. Okay? So you found that since you're using a first order autoregressive process, or it's a first order difference equation, so there's only one value of b which you get, okay, by solving this way. So you get this value of b. Now b here is called a characteristic root of this particular equation. Okay? When you're setting it equal to 0, if you take only this equation, b plus 3 is equal to 0. Okay? Just ignore this part. It disappears anyway. If you take only b plus 3 is equal to 0, Here b is the characteristic root of this equation. Now once you solve for b, you get a single value of b and you're able to move forward and find the general solution. Now what happens in higher order systems or equations? Yeah.
And basically b is equal to minus a, right? So b is equal to minus a is only for a first order difference equation, or like it's like a general rule.
No, it won't be a general rule. That's what I'm trying to tell you, that for higher order systems, okay. Now what I want you to do is try and write for a second order difference equation. Okay, so you have yt is equal to, just do it for yourself now, it will help you to understand the next part. So write an Ar2 process, basically, the general notation. Once you've done that, set up the complementary function for this. Okay. I hope you're following the instructions because it will help you to understand the next part. So first write an Ar2 process, equation for an Ar2 process, then set up a complementary function. Okay. Once you do that, write that equation where you have b minus whatever in brackets, b plus or minus. Okay, once you're finished, can anyone tell me what you're getting? What you wrote and what you got?
It is coming out to a quadratic equation.
Yeah, okay. So in brackets, basically you will get a quadratic equation, right? Can you just read that out?
It would be 1 minus b square. I think I'm wrong.
Tell me what your Ar2 process was, what you wrote for the equation.
I wrote a b to the power of t minus a b to the power of t minus 1, t plus 1, and a b t plus 2. So I did minus 1 and minus 2, so it would be minus 1 and minus 2 in the quadratic equation.
Okay, wait, let me just type here and then you'll use this to solve, okay?
Will it be kind of like 1 plus b square is equal to 0?
Well, yeah, that's what I'm getting. 1 plus b plus b square is equal to 0, and then we solve for b.
Yeah, basically you will get a quadratic equation. Okay? So later on you'll do this. Yeah, I've typed and I've sent it to you. So later after the class is over, you'll use this. So when you're setting up the complementary function, what you'll be doing is shifting these yt terms to the left hand side. Then yt will become ab raised to the power t. Okay, then you will have minus abt raised to the power t minus 1 minus a2 abt raised to the power t minus 2. Okay, this a1 a2 both have to be there in that equation. Set it equal to 0, then you'll get one whole equation in brackets which will help you to solve for b. Okay, but basically you will be able to get a quadratic equation. Okay, since you're looking at an Ar2 process, you will get a quadratic equation. Now similarly, if you have higher order systems, okay, where the lag order is greater than 2. So in general, if you have an nth order difference equation, okay, where there are n lags, then you will be setting up the complementary function this way. Okay, just look at the notation. I'm sure you'll be able to follow it. I runs from 1 to n, so there'll be n lags here. Okay? So when you're doing this, finally the term that you get in brackets, okay, that is called the characteristic equation. So if you look at the quadratic equation that you came up with in the Ar2 process case, okay, it would have had this form: b square minus a1 b minus a2. Okay, yeah, minus a2. This would have become a2 2 minus 2, so 0. So this becomes 1. Okay, so b square minus a1b minus 1. So that is something you would have come up with. That would have been the characteristic equation for your higher order system. Okay, so that if you solve that, then you would have been able to find the value of b. Okay, but in the case of the second order difference equation, for example, for an Ar2 process, since you got a quadratic equation, after solving you would have got two values of b. Okay. Similarly, this here, you can see that the order of this equation is n. Okay, so or b is raised to the power n. So if you solve this characteristic equation, you would have got n roots, okay, or n values for b. So we say that there are n characteristic roots. I hope you all have been able to follow me. Anyone has any doubts?
No, ma'am,
Ma'am,
B will
I'm
also
stuck
be coming
somewhere.
there, right?
Okay.
Ma'am,
Can
like in this equation, the second
yeah,
equation which you have written here, is the
yeah.
B missing from A2
No, b is raised.
to the power n minus 2? I guess B will be coming.
Yeah. Correct. Yeah. Okay. In only in the case of the Ar2, it will be. It won't be there. Yeah. B should be here. I'll just correct it when I'm writing it later. Okay? For the last term, you will not have B, since it's an nth order equation. Anyone else?
Ma'am, one thing, if you are doing a second order equation, would that quadratic equation would be 1 minus b square or 1 plus b square?
See, did you see what I typed in the chat box?
Yes, I did. I am trying to solve it through that one.
Okay. Just take a minute, all of you, and just use that and write the complementary function part and write this characteristic equation. Okay, then we'll discuss. It's important that you understand. That's why I'm waiting. Okay, have you all finished? Just let me know once you've finished.
Ma'am, I understood the process, but I am not able to get, I don't know what is the correct answer.
Okay, so for the case that I typed in the chat box, what you will
Yes.
get is b square minus a1b minus a2. Okay, that will be the term in brackets. and outside brackets you'll have AB raised to the power t minus 2. That
T
term
minus
will
2. Okay.
vanish. Okay, it's equal to 0 anyway, so that term will go. So you'll be left with only b square minus a1b minus a2. Okay, so that is your characteristic equation. Now since it's a quadratic equation, you will have two roots. Okay, two characteristic roots. So you'll get two values for b if you solve. Okay. Now similarly for an nth order equation, you'll get n characteristic roots, okay, or there'll be n values for b, which you can designate as b1, b2 up to bn. Okay.
Okay, ma'am, got it.
So if you do this for higher order processes, in every case, okay, if you don't believe me, you can try it out for yourself, but in every case, you'll find that there will be n characteristic roots depending on the order of the equation that you've chosen. Okay. So now there are certain properties for these characteristic roots, and if they are satisfied, only then a particular time series will be stationary. So this is important because many times when you're reading articles or when you're having discussions, or if you refer to other notes, you will come across this concept and you might be wondering what it is. So if I don't teach you at all, it'll not that it'll take away that much from the subsequent part of the course, okay, but you will feel that you have missed out and maybe there was some sense of incompleteness in the course itself if I don't discuss this part. That's why I'm going through it. Okay, but you will not be quizzed on this. So just keep in mind that this is the characteristic equation, okay, that term which you get in brackets where you have b, all the b terms collected together. Okay, this I'll correct later when I'm sharing the note. So you'll have n characteristic roots in an nth order equation. Now just imagine there's a graph, okay, where along the horizontal axis you have real numbers, okay, and along the vertical axis, just imagine the labeling, okay, you don't have to actually imagine the numbers itself. So along the horizontal axis you have real numbers, and along the vertical axis you have imaginary numbers. Okay, so along the y-axis you have imaginary numbers. Now just imagine that a circle is drawn with the origin as the center. Okay, so a circle is drawn on this graph which has a radius of 1. Okay, and the center of the circle is this origin. Okay, so the radius of the circle is equal to 1. Now, if all these roots, okay, which you have calculated, if you have an nth order difference equation, once you find the roots, if all these characteristic roots lie within this circle, okay, which has a radius equal to 1 or unity, okay, then it is said that the time series will be stationary. Okay. So generally it is said that all the characteristic roots have to lie inside the unit circle. Okay, you will come across this term very often. Only then a time series is said to be stationary. Did you all follow this part? Would anyone like me to repeat it?
No, ma'am.
I was
Neil, go ahead.
Yeah, I was going to say if you could repeat it. I'm going to assume that all of them have to be less than 1, but if you could just repeat that.
Yeah. See, just imagine a graph with along the x-axis you have real numbers, and along the y-axis you have imaginary numbers. You don't actually think of the numbers because it will become very complex. So now just think that a circle is drawn on this graph which has a radius equal to 1, and the center of this circle is the origin. Okay? Now all these characteristic roots, if you have an nth order equation, all the characteristic roots have to lie within this circle. Okay? So generally it is said that for a time series to be stationary, all the characteristic roots have to lie inside the unit circle. So unit circle basically means a circle with a radius equal to 1, which is plotted on this sort of a graph, where one axis has real numbers, the other axis has imaginary numbers. Okay. Now there are certain rules, okay, that we need to understand about this. Now how do we determine or make sure that these characteristic roots lie inside the unit circle? Okay, generally it's very cumbersome. You can already see that for an nth order equation it will be very difficult to find all the characteristic roots, and generally nobody sits and calculates all these characteristic roots. Okay, even just like how we use the lag operator, we cannot simplify this very easily, okay, to find all the n roots for a characteristic equation. So generally some software is used to find all the characteristic roots, but if it is still too cumbersome, and generally people don't do this, okay, they don't even use software or anything like that. So there are some simple rules of thumb you can use to find out if all the characteristic roots lie within the unit circle. Okay? So in an nth order equation, a necessary condition for all characteristic roots to lie inside this unit circle is that the sum of all the autoregressive coefficients have to be less than 1. Okay, so this is a necessary condition for all the characteristic roots to lie inside the unit circle. Now, what is the sufficient condition? That if you sum up all the absolute values of the autoregressive coefficients, that sum should be less than 1. Okay? So if these two conditions are satisfied, then we say that the time series will be stationary. Okay? Now, if at least one characteristic root is equal to 1, okay, then you will find that the sum of all the autoregressive coefficients will be equal to 1. Okay? I don't know how it happens. I haven't done the math myself, but this is a general rule of thumb. Okay? That if at least one characteristic root equals unity, then you will find that the sum of the autoregressive coefficients will be equal to 1. So if you ever find if you are given a difference equation and you find that the autoregressive coefficients are adding up to unity, then you can be sure that at least one of the characteristic roots is equal to 1, okay, or unity. And such a process, if there's a sequence of such characteristic roots, okay, then such a sequence is called a unit root process. So this time series is not stationary in that particular case, okay, where even at least one of the characteristic roots, if it's equal to 1, then we say that the time series is not stationary because it has a unit root. It's called a unit root process. Yeah, I hope this was clear to everyone. Okay, so if a time series is not stationary, we call it a unit root process or a non-stationary process. So simple rules of thumb that will help you identify whether all the characteristic roots lie inside the unit circle so that the time series itself is stationary are these. Okay, necessary condition for all the characteristic roots to lie inside the unit circle is the sum of the autoregressive coefficient should be less than 1. Sufficient condition is if you take the absolute values and sum them up, they should be less than 1. Yeah, I hope this was clear to everyone. Anyone has any doubts? This is just for your understanding, okay? Because many times you'll hear these terms being used, and if you don't know what it means, then you'll feel like there's some gap in your knowledge. So I'll quickly just come back to today's class again. I mean, the notes that we were discussing earlier. If anyone has any doubts, please ask me. Okay, you might find all these derivations a little tedious, but once you understand it, it will become very easy for you and you'll understand what you're doing. Next week, we'll do the practical, so then it will become a lot easier for you to understand. Okay, now let's look at an Ar2 process again. Now we are omitting the intercept term because it generally has no effect on the autocorrelation function. Okay? Now let's derive the autocovariances using the method of Ewell-Walker equations. Okay? So this method is used to basically simplify the calculation of the autocorrelation coefficients and the autocovariances themselves. So just take the first order, Ar2 process itself as it is. Now what you need to do is multiply both sides of the equation. Okay, multiply both sides of equation 1 by yt minus s, okay, where s assumes various values running from 0, 1, 2 and so on. Okay, and then take expectations on both sides of the equation again. Okay. So I've just shown you to help you understand. So first take s is equal to 0. So you're left with yt. Okay, so we're going to multiply equation 1, the entire equation by yt. Okay, so you end up with this equation. Then take expectations of that. Okay, so you end up with equation number 2. Now similarly for equation 3, what we have done is s assumes a value of 1. So you multiply equation 1 both sides again by yt minus 1. Okay, that's what we have done here. And keep doing this process. Okay, keep repeating this process up to s lags. Okay, now generally when you're doing the practical work or when you're using any software, the practice is to use about 1/4 of the entire sample that you have to calculate these autocovariances and autocorrelation function. Okay, so you'll be using t by 4, where t is the total number of observations. So that is generally done, but when you're doing the practicals, you won't have to do all this. It will be calculated for you by the software itself. Okay. So just multiply this way and take expectations. Now by definition for a stationary series, okay, the covariance between yt and yt minus s, okay, is denoted by gamma s. And these are certain assumptions that we make. Expectation et yt is equal to sigma square. Okay. Now the variance of et is equal to sigma square itself, and yt also has a variance of sigma square. Okay, so generally if you take expectation et yt, you will get sigma square. Now expectation et yt minus s, okay, is equal to 0. So these are certain assumptions, and then we are going to use this to find the autocovariances and then the autocorrelation coefficients itself. Okay. Now using these equations that we formed, okay, these are called the Ewell-Walker equations. So using these equations, okay, let's take the first one. Now if you take expectation yt, okay, this is nothing but the variance of yt. Okay, so you get gamma 0 here. Okay. So gamma 0, then here this is the covariance between yt and yt minus 1. Okay. So you get gamma 1 here. Okay. This is what is shown here. So you will get A1 gamma 1. Similarly, this is the covariance between yt and yt minus 2. So you get gamma 2. Okay. You're just using the general notation. And expectation et yt is equal to sigma square. Okay. So when you write out equation 6, you're just using the general notation here. Okay. Similarly, if you do that for equations 7 and 8, okay, this is what you get. If you want to just take a look at equation 7, okay, so here you will get gamma 1, here you will get gamma 0, here you will get gamma 1 again, okay, and this will be 0. Okay, so gamma 1, gamma 0, gamma 1, okay, this is just what I discussed. So the same way for each of these equations, okay, using all these Ewell-Walker equations, you can write the general notation and find out what the autocovariances are. Now, just divide equation number 7 and 9 by gamma 0. Okay, so if you take equation...
Ma'am,
yeah.
Can we call it a day right now?
Yes,
yeah,
ma'am.
okay.
It's difficult to get, understand now that the gamma thing.
Yeah, sure. Okay. Just keep this in mind. Try this for yourself. I'll circulate these set of notes. Okay, up to this point. Just take equation 7 and 9 and divide it by gamma 0 and just come up to this point. Okay,
Okay, ma'am.
Try and do this for yourself, and then we'll discuss more in the next class. Okay. So next week, I'm sure you all will be tired of all the derivations. So next week, on Friday, we'll try and complete our discussion of all the derivations and so on. And then on Saturday, we'll do some practicals so that you can actually see whatever you're learning in action. Okay?
Ma'am, any book that we should refer to, or your notes are enough?
You can refer to Rousseau and Campbell, Lowe, and McKinley. Okay, you can refer to these books. Then there's a book by Hamilton which is somewhat it follows matrix notation, so you all might find it harder. But in general, those two books will be fine, and for the rest, you can follow the notes. Okay? So if you have understood the lectures and then you follow the notes, it should be easy for you to understand what we're doing.
Yes, ma'am. But if you have time while circulating the note, please mention the book name once again. Since
Okay.
okay.
I'll share the syllabus with you all. The syllabus itself. So that has the list of books. You all can go through that and.
Okay. Thank you.
Yeah. Okay. So if you all have any doubts or questions, note them down. We'll discuss in the next class. And next class we will do practicals so that you all are not exhausted by just the derivations. Okay. So please download R and R Studio. Okay. We'll try and use mostly R Studio itself for the practicals. Okay. So we'll meet in the next class.
Next Friday.
Yeah, next Friday.
Thank you, ma'am.
Thank you for your time.
Thank you, ma'am.
Yeah, welcome.